The crystal field theory was proposed by Hans Bethe and Van Vleck. This theory gives a much more satisfactory explanation for the bonding and the properties of complexes than the valence bond theory. The crystal field theory is based on certain assumptions. The interaction between the metal ion and the ligand is purely electrostatic. That is, the metal-ligand bonds are 100% ionic in nature. Negative ligands are treated as point charges, and neutral ligands are treated as dipoles. Thus, the bonding in the complex may be an ion-ion interaction or an ion-dipole interaction. The 5d orbitals in an isolated gaseous metal atom or ion are degenerate. That is, they all have the same energy. However, when the ligands approach the metal ion to form a complex, the electrons in the d orbitals of the metal will be repelled by the negative charge or lone pair electrons of the ligands due to the repulsion between the like charges. As a result, the energy of the d orbitals increases and the degeneracy of the d orbitals is lifted. It results in the splitting of the d orbitals. The pattern of splitting of the d orbitals depends on the number of ligands and their arrangement around the central metal atom or ion. Let's look at the application of the crystal field theory to octahedral complexes. In octahedral complexes, the metal ion is at the center of the octahedron, and the 6 ligands lie at the 6 corners of the octahedron along the 3 axes X, Y, and Z as shown here. The approach of the ligands towards the central metal ion is considered a 2-step process. In the first step, it is assumed that the ligands approach the metal ion spherically, that is, at the same distance from each d orbital. At this stage, the energy of all the d orbitals is raised by the same amount. That is, the 5 d orbitals still remain degenerate. The average value of the energy of the d orbitals at this stage is taken as 0, and this is called the Barry center. However, out of the 5 d orbitals, 2, that is, the dx square minus y square and dz square orbitals, which are collectively known as the EG set of orbitals, are oriented along the axes towards the direction of the ligands. Thus, the EG set of orbitals will experience more repulsion than the remaining 3 d orbitals. That is, the dxy, dxz, and dyz orbitals, which lie in between the axes. These 3 d orbitals are collectively known as the T2g set of orbitals. Consequently, the energy of the EG set of orbitals increases, while that of the T2g set decreases relative to the average energy in the spherical crystal field. Thus, under the influence of the ligands, the degeneracy of the 5d orbitals of the metal ion is lost, and they are split into two groups of different energies. This effect is known as crystal field splitting. The extent of the splitting in energies is represented by the symbol delta O. The subscript O indicates octahedral geometry. Due to this splitting, the energy of the two Eg orbitals will increase by 3/5 of delta O, while that of the three T2G orbitals will decrease by 2/5 of delta O. The magnitude of crystal field splitting depends upon the field strength of the ligand and the charge on the metal ion. Ligands that cause only a small degree of crystal field splitting are termed weak field ligands, while ligands that cause a large splitting are called strong field ligands. In general, the common ligands can be arranged in ascending order of field strength as shown here. The order remains practically constant for different metals, and this series is called the spectrochemical series. It is an experimentally determined series based on the absorption of light by complexes with different ligands. Now, let's assign electrons in the d orbitals of the metal ion with d4 configuration in the octahedral coordination entities. Obviously, the first, second, and third electrons occupy the low-energy T2G orbitals in accordance with Hund's rule. However, for the fourth electron, there are two possibilities. The first possibility is that it may enter a T2G orbital and pair up with an existing electron there. The other possibility is that it may enter the higher Eg orbitals. The exact path followed by the electron depends on the relative magnitude of the crystal field splitting, delta O, and the energy required for the electron pairing in a single orbital, that is, pairing energy B. If the crystal field splitting energy is less than the pairing energy, then the fourth electron enters one of the higher energy Eg orbitals, giving the configuration T2G3 Eg1. Ligands for which the crystal field splitting energy is less than the pairing energy are known as weak field ligands. The complexes formed with these ligands would be high-spin complexes. If the crystal field splitting energy is higher than the pairing energy, then the fourth electron enters a T2G orbital and pairs up with one of the electrons, giving the configuration T2G4 Eg0. Ligands for which the crystal field splitting energy is higher than the pairing energy are known as strong field ligands. The complexes formed with these ligands would be the low-spin complexes. Now, let's look at the crystal field splitting in tetrahedral complexes. The approach of the ligands in a tetrahedral field is as shown in the figure. You can observe from the figure that the ligands interact more with the T2G orbitals than the EG orbitals lying between the axes. This is because the T2G orbitals are oriented along the direction of the approach of the ligands. Thus, in tetrahedral splitting, the T2G orbitals are of higher energy, and the two EG orbitals are of lower energy. You can say that the d orbital splitting in tetrahedral geometry is exactly the reverse of octahedral splitting. The crystal field splitting in tetrahedral complexes, which is denoted by delta T, is smaller than that of octahedral complexes. The difference in energy can be represented by delta T is equal to 4 by 9 times of octahedral splitting. This splitting energy is not large enough to force the electrons to get paired up. Thus, low spin configurations are rarely observed.